now we'll do the flux through the top and bottom faces. Let's do the top face first. Let's think about our area first. So here's our box. We already know our electric field because that was given in the first part. The X is variable again because we're going to have to add up and cross the entire box. So let's think about our area element. Along the top face, let's pick a small rectangle as our area element. The direction is straight out of the cube, so it points upwards. That's going to be in the y direction. So our dA, our area element vector, is going to have a magnitude, which is going to be length times width. The length is along one edge of the cube, that's A. The width is a little bit along the x direction, that's dx. And the direction is straight up out of the face, that's the y direction, or j hat. So there's our area element. So now let's put this together with our expression for the electric field. So this is the y part of the area element. The x and z parts are 0. So when we do our electric flux, we get the integral of Ex times dAx, that term is 0, plus the integral of Ey times dAy is 0, that part is 0, and the integral of Ez times dAz, that part is 0. So the net flux through that top face is actually 0 because each of these terms are 0. dAx is 0, Ey is 0, dAz is 0, so the entire flux turns out to be 0. So that deals with the top face. Now let's do the bottom face. We'll just quickly redraw that cube again. A little bit hard to draw in 3D, but hopefully you can get somewhat of a picture. So there's our bottom face. There's the area element. We'll stick straight out of the cube. dA points down. So dA, area element vector, which has a magnitude and a direction. The magnitude is going to be the length times width. The length is along one edge of the cube. The width is a little bit along the x-axis, so it's dx. And the direction is straight down, so that would be the minus y direction or the minus j direction. So that's our y component, dAy. dAx and dAz again are 0. So let's think about what is our net flux in this case. So our flux through the bottom face is going to be the integral of Ex times dAx, that term is going to be 0. Ey times dAy, that term is going to be 0. Plus Ez times dAz, that term is going to be 0. So the flux through the bottom face is going to be 0. So that means we don't have any electric field lines cutting through the top or the bottom face. So the next part of the question says find the net flux. The net flux is what we get when we add them all up. So let's just do a reminder of what we had. We'll add up the flux through the front face, which is 10, plus the flux through the back face, which is minus 10, plus the flux through the right face, which was 20, plus the flux through the left face, which was 0, plus the flux through the top and bottom, which are also zeros. That gives us 20 newtons per coulomb times meters squared. And then the last question is, does this tell you anything about the charge in the box? Something to think about as we build towards Gauss's law. We do have a net flux. It's positive, which means the electric field lines go out through the surface. That's what a positive flux means. If we have a net number of lines going out through the surface, some lines must be starting inside the surface. So our net flux is greater than 0. So some lines must start inside. If some lines start inside the box, there must be a positive charge in the box. So that's what we can learn from finding the net flux around here.